Hello and welcome to the 34th lecture in this series. So towards the end of last class we had started talking about integral curves and ordinary differential equations in the presence of a vector field. So let me quickly recall what we were trying to do. Well, the defining property, so let's say we start with a vector field on a manifold M. A smooth curve in M is said to be an integral curve of x starting at P if its velocity vector at time t happens to be the vector field, the value of the vector field at that point. And the starting at P just refers to the fact that at time t equals 0, I have sigma 0 equals P. Right, and the fundamental theorem is that for any point there exists epsilon greater than 0 and an integral curve of x which starts at P. This integral curve is unique. In fact, something slightly stronger holds, which I will state in this lecture. So, but in any case, to prove this, the idea is to first transfer the setup to Euclidean space, to an open set in Euclidean space, and see what exactly the integral curve equation means. So here we took a chart around P, and the first thing is that we transfer the vector field on U to a vector field on U1 by this equation here. And I had remarked that in general, when you have a smooth map between manifolds and you have a vector field on the domain, it is not possible to use the derivative of the map to transfer the vector field on the domain to a vector field on the target. As an extreme case, one can consider an extreme case is that of f equal to constant. So the whole domain is getting mapped to a single point. Now so the derivative of the map is 0, and so no matter what vector field you start with here, you will get 0, and which will be, so of course one has the 0 vector field on the target, but that's not what one wants. Even if f is not the 0 map, the problem, there are two problems essentially which I discussed last time. The map not being surjective and the map not being injective. Well, if it's a diffeomorphism, then one can proceed like this, what I have done here. Actually, so here I have to make a small correction. So this, I'm starting at a point y here. So then I go via phi inverse, and then, well, no, it's I guess it's fine. So I go via phi inverse, end up at phi inverse y, use the vector field at that point, x at phi inverse y, then use the derivative of phi and get back to y. So, right. So that's okay. So as usual, one has to be careful about smoothness. However, we have seen this before. It can be checked that this y is smooth on U1. To see this, what one would do is, one would, so let f be a C infinity function on U1. So we want to consider this function y of f as a function of, so y going to this. So I want to see if this is smooth. Well, this is one way. Other way is just to express this in as coordinate functions and so on. So in fact, right, okay, let's do this. One can do it both ways. So I have a function f here. This is phi. This is u sitting inside M. So this by definition is whatever I wrote down here, d phi at phi inverse y acting on x at phi inverse y. The whole thing should act on f. And exactly like a couple of classes ago, this using the definition of the differential of phi, this is actually equal to x at phi inverse y, and then f composed with phi, the phi coming from here, x at phi inverse y of this. Well, this can be written as a composition of two maps. One is, so let's define two maps. So I want to define a map alpha from, this is from U to R by alpha equals x, alpha at x equals x at x of f composed with phi. This is one map, and the other map is phi inverse. So then this map y going to capital Y subscript y f, let's call this as I've been calling it G. So let's continue doing that. Then G equals alpha composed with phi inverse. And we know that, so the vector field being smooth by definition means that right, so the smoothness of the vector field by definition means that this alpha is a smooth map, and since phi inverse is smooth because phi is a diffeomorphism, therefore G is smooth. Right, so it's immediately clear that this transferred vector field on U1 is also smooth. Well, right. Now, the other thing to note is, note that sigma from an interval to U1 is an integral curve for or of y if and only if so again the picture is like this. So this is phi u1. So if I have an integral curve sigma here, so literally sigma would be a map from here to here. So I can use phi inverse to get a curve, smooth curve in U. And so the claim is that sigma is an integral curve of y if and only if phi inverse composed with sigma is an integral curve actually let's say instead of saying for, let's say of integral curve of y, integral curve of x. This again follows just from the definition of y. So let's see one way. I mean, let's do, yeah. So suppose I start with an integral curve of y. Let's see why this is an integral curve of x. So all I have to do is I have to differentiate. So I have to look at phi inverse composed with sigma prime at t. And I want to check whether this is actually equal to x at the corresponding point, x at phi inverse composed with sigma t. So now it's just a matter of applying chain rule. So the chain rule tells me that this equal to d phi inverse at the point sigma t acting on sigma prime t. Well, actually it tells me that this is equal to d phi inverse sigma t composed with d sigma acting on del by del t, but that's the same as this. The way we define sigma prime t, it follows that this is left hand side is the right hand side. Right. So now we know that sigma is an integral curve of y, therefore I can plug that in here, d phi inverse sigma t. So and so this is y at sigma t. Right. So now, but y at sigma t by definition was, so let's recall, y at sigma t was just transferring, obtained by transferring the vector field x to this. So d phi inverse d phi at phi inverse of sigma t, and then x at phi inverse sigma t. So now we just right. So this is, should be in brackets actually. So now you just compose. So you just look at these two terms. There's d phi inverse at sigma t and phi of this. So the chain rule tells me that this composition is exactly identity. So I'm left with x at phi inverse of sigma t, which is exactly what I wanted. So phi inverse sigma t, phi inverse composed with sigma prime is x at phi inverse composed with sigma. So this statement, so we have just checked that integral curves go to integral curves under this just by taking phi inverse. So with all that in hand, now let us finally look at what the integral curve equation looks like. So we are now, we now have a vector field on an open set in Rn. As I pointed out last time, a vector field on an open set in Rn is the same thing as, i.e., a smooth map capital F from U1 to Rn. Vector field on an open set in Rn is the same thing as a smooth map on this. So, and now let's see what the equation. So the integral curve, let gamma from AB to U1 be an integral curve of this y. So d sigma by definition, d gamma by dt, this is gamma prime t. Gamma prime t equals d gamma by dt is supposed to be y at gamma t. Now, if one thinks of the vector field as the smooth map, then this is the same as f of gamma t. So this is the usual going back and forth between derivations and elements of Rn that is going on here. When I normally talk about vectors and tangent vectors and vector fields, at each point one thinks of them as derivations. At the moment you are in Rn, I can think of them as elements of Rn. That is this f of gamma t. So in effect, what we have is d gamma by dt equals f of gamma t. i.e., gamma is an integral curve of if and only if gamma is a solution of n. Now this thing here in the box is of course I've written it as a single equation, but recall that gamma is a map from, it's a function of one variable, but the target is an open set in Rn. So actually gamma t is gamma 1t, gamma nt. So there are n functions of one variable, and this likewise f of x is f1x fnx. If one uses this coordinate expansion of gamma and f, then this thing here is equivalent to d gamma 1 by dt equals f1 gamma t dot dot dot, and then d gamma n by dt equals fn gamma t. So in effect we have a system of n ordinary differential equations, and right, if and only if gamma is a solution of an ODE system. And the fact that the right hand side just depends on gamma t is and does not involve t as a separate variable is this is usually called an autonomous system of ODEs. So but let me just stick to the phrase ODE system to mean this. So what we have done is we have reduced the problem of existence of integral curves to the existence of solutions to ODEs, and I have omitted this starting point, but we can retain that. And here for example, even though I have not mentioned that, so gamma 0 equals, so if we want an integral curve starting at p, remember that phi inverse sets up a correspondence between integral curves in u1 and u. So if I want something starting at P, I should start here at phi of P. So gamma 0 equals phi of P is the, let me add this as a box here. So here it would be gamma 1 0 equals phi 1 of P, gamma n 0 equals phi n of P. So the whole point is to see that this the notion of an integral curve is the same thing as a solution to a certain ODE system. It's completely equivalent, and of course the point is that one should be able to say something about this ODE system, and for this we have the powerful existence and uniqueness theorem of Picard. So let's state this. Let U1 contain, I'll just keep the same notation as I had before, be an open set, and f from U1 to Rn a smooth function. Given x naught in U1, there exists an interval, an open interval, let's just call it I naught in R with 0 in I naught, and an open set V which contains x naught and it's contained in U1 such that so this is U1, x naught is some point, V is a smaller open set, and I want to claim that for any point inside this V such that for any x in V, there exists a smooth solution to there exists smooth curve sigma from this interval I naught to U1 with satisfying d sigma by dt equals f of sigma t and then sigma 0 equals x. So what I am saying is slightly stronger than what I had stated earlier in the context of integral curves. Here what I am saying is that if I take any point x naught and there exists a neighborhood of x naught which I call V such that for any point in the neighborhood I can find a solution to this equation starting at that point x, and that solution is we can assume it's defined on the same interval I0. So this interval I0 is the role of that is at this stage it may not be clear, but it's very important. It typically very much depends on which point you are at. At some points the solution may be defined for long time interval, at some point it may be very short interval. So here we are saying that as long as we are close enough to a given point, all the intervals on which the solutions are defined, we can assume that they are all defined on a common interval satisfying this. This is one statement. Second statement is that any two solutions, so let's call this star, any two solutions to star agree on their common domain. So in other words, if I have a solution to this system with the same initial data sigma 0 equals x, if I have two solutions, both of the domains will have to contain 0 because I need to make sense of sigma 0. So if I have two solutions, then the domains may be different, but if you take the intersection of the domains, that will be an open interval containing 0. On that they both agree. And the third thing is that this is called smooth dependence on initial data. So let us define a map from the map phi. No, I've already used phi, so let me use some other notation. The map, let's say G, from this V cross that I0 to U1 defined by so here in the in step 1 I said there exists a smooth curve sigma. Now this sigma is solution to the differential equation and it starts at x. So let's keep track of that x by putting a subscript here, sigma x. So I'll just put a x here. So now this map G is defined by gxt equals sigma x t. So in other words, what this map is doing is easy to explain. You start with a pair x comma t. Well, you just look at the solution which starts at x, travel along that for time t, that is this. So the claim is this map is smooth. Now this is stronger than saying we know that each solution to this differential equation is smooth, but what we are saying here is that when we regard the solution not just as a function of, here also I should put an x, when I regard the solution not just as a function of t, but also of the initial starting point x. So for this new g, x is also a variable. Even then, there is smoothness. So as you change the starting point, then the solutions sort of, you get different solutions. They all change smoothly. That's what this is saying. Right. So this is the fundamental theorem, which I'm not going to prove, and let's assume this. Once we assume this, then the integral curve setup becomes a simple corollary restatement of this. It's not even a corollary, it's just a restatement. So for instance, what we did was we started with a manifold. We took a chart, transferred the vector field to an open set of subset of Rn. Then we saw that we get an ordinary ODE system, namely this. Now we apply Picard's theorem to conclude that there is a solution to this with the given starting point. And we transfer it back to the manifold via phi inverse to get a integral curve for the original vector field.